Greetings of the day. I am Gayathri Aditya, working as Associate Professor and Head of the Department of Planning at Nitte School of Architecture, Planning and Design. Today I was asked to talk about appropriate design, technology, construction, and materials in the field of building architecture. So I thought of talking on a contemporary building material that generates electricity. So most of you know photovoltaics alias PV. So the topic is evaluating the viability of building integrated photovoltaics, especially for Indian conditions. So special focus will be on the thermal performance and the climate responsiveness of PV. So we all know the imminent reality of global warming and consequent climate change, in addition to impending risks of oil shortages, is driving the increasing reliance on renewables. India's geographical location luckily renders it with ample of solar energy potential, which is around 4 to 7 kilowatt hour per meter square per day. So that means 2,300 to 3,200 sunshine hours annually. So if we can appropriately harness the solar energy, this has adequate potential to support the energy demands of the country, and the on-site distributed power generation using solar is seen as a sustainable green alternative. Given the diverse nature of human settlements, like we have scattered, low-rise to dense high-rise, one of the unexplored avenues of harnessing solar energy is electricity generation using PV. So PV is viable for on-site distributed power generation, offering advantages. You have the size and scale variability, modularity, and integration into buildings. So given these advantages, and you can put PV in your building envelope, like for walls, fenestrations, roofs, and skylights. But the prime function of a building is to provide thermal comfort for conducive working and living conditions, with the building envelope acting as an interface regulating the thermal interaction between the external and the internal environment. To be energy efficient as a building envelope, BIPV would need to passively regulate the responsiveness of the building envelope to the external environment, which is predominantly the solar radiation, wind patterns, rainfall, ambient temperature, and humidity. Right? So, and this changes from geographical location and local characteristics. That's the microclimate. PV integration is generally, why do we do it? To get maximum electricity generated. So this depends on the solar exposure, that is the slope and orientation, the system sizing, wind patterns again, and dust conditions and maintainability. These factors need to be intertwined, right? Like for the climate responsiveness, you have set of factors and you have set of factors for the PV performance. So these has to be matched. However, like the climate responsive building design may infringe upon those required for PV performance. So this whole study is to understand that aspect. Okay. And you can't compromise on PV's performance because it has a high initial cost, and it is crucial to ascertain PV's ability to support societal energy demands. So now the whole study is about addressing concurrently the design requirements of energy efficient building performance, effective PV integration, and social feasibility. So in this, we have taken a case study from India and have worked on that. So now jumping into the presentation. So having in the beginning, as mentioned, the problems are you have global warming, climate change because of that, and you have impending risks of oil shortages. Then you have the Indian electricity scenario. There are a lot of losses, which I'm going to deal in the next slides. and you have land and building problems. So all this shows only one way, that's our reliance on renewable energies. So quick snapshot of the electricity scenario in India. We are the 5th largest producer and 6th largest consumer of electricity. We have an installed capacity of 200 gigawatts. And mostly we use 59% of coal. Coal-based thermal power plants are the main producers of electricity. And we have 600 million people have no access to electricity. The energy demand traditionally dominated by domestic sector, raised because of the ownership of appliances. And talking about the centralized electricity generation issues, we have supply and demand deficit. So we need almost like, we need to increase it 4 times by 2040 to meet the demands. Inefficient transmission and distribution. We have losses. So once the coal and power is generated at the coal power plant, thermal power plant, by the time it reaches your house, there is 33% of loss in the electricity. And we are not a coal-rich country. We have to import 28% of our coal, which is used for, is imported from Australia. And we have land use issues like mining, waste disposal, transportation, construction, commissioning time, modification of soil strata. So we have all these issues which are coming under the land use. Another small snapshot on the domestic sector. So 40% of the energy is expected to double by 2040. Right? Domestic energy consumption has increased by 100 terawatt hour in 12 years in 2012. 20 billion square meters of new floor area is expected by 2030. 67% of the housing infrastructure for 2030 still needs to be constructed. This poses a heavy demand on land and energy resources. What is the need of the hour? So can we have an electricity solution that is decentralized and which can integrate well with the domestic sector, which has the solution that can reduce the impact on land? Land has high potential, it's very expensive. Finally, the electricity solutions that are truly green. So as mentioned, we are solar rich country. So on an average of a 3 kilowatt rooftop PV, if I install on a 20% of the total households, that is 425 million households, by the year 2070, these produce 90 terawatt hour. PV is noiseless system as against a windmill. If you put on your rooftop, you can't bear that sound. And it has very low maintenance. The panels has to be cleaned, that's it. Nothing, no other maintenance cost is incurred. PV in buildings can save additional land resource. So this is a study done by one professor at IIT Bombay. So he made a calculation for one of his in one of his publications. So an estimate with 1.7 billion by 2070 India's population and 425 million houses are required with 1,840 kilowatt hour per year. The per capita electricity need, the total electricity needed is simple math. Okay, it's 3,128 terawatt hours per year. So approximately, if I say 30 square meters is available for every household, and I can install a 4 kilowatt PV that can produce around 5 megawatt hour per year. So beyond this, you can just multiply these numbers, simple mathematics, you get the answer. It's such a brilliant solution, right? But then where is the problem? What is stopping us from using this? Why are we not using it? So just before getting into the details of it, we can understand like the components of the PV panel and how does this energy, the sun energy becomes the electrical energy. So the smallest unit of the PV panel is called a cell, and a bunch of cells is called a module, and a couple of such modules is called an array. So for this solar PV panel, you need solar energy falling on it. And to that to reach to your house as electric, so you need some more electronics components into it. So that is called balance of system, is a technical term. So when the sunlight falls on the PV panel, this gets its DC energy which is produced. And that either can be, it is converted into AC, or the same DC can be stored in the form of a battery, or can be put in the grid. You can either use it for your house or send it to the grid. The excess energy can be pumped into the grid. So this is the simple flow of the energy. So there are two ways we define how we install this. So when you put the PV panel on just top of your roof, which is already like a concrete slab you have, and you put your PV panels on top of it, it's called building applied photovoltaics. Whereas building integrated is when your PV panel becomes the building element itself, like a roof, a shading, or a wall, or an opening, a window. So we call it as building integrated photovoltaics. So the simple definition, the simple logic here is when the PV is the interface between the outdoors and the indoors, we call it as building integrated. So like what are the factors, what affects the PV performance? The more sunlight, the more electricity which is generated, right? That's simple formula. But there are certain things like as the temperature of the panel increases, your efficiency of the panel also drops. So you have environmental factors like dust should not fall on the panels, the bird droppings, shading will affect the PV performance. That is the environmental factors. Then you have installation factors. You should have like shade free, and you should have the tilt and the orientation, how you place the PV panel also affects the PV performance. Not only that, the technical factors like the technology, what kind of technology. There are 3 generations PV panels available in the market. So the first generation is still the market leader. That's called monocrystalline PV. And then you have the organic PV, dyes, paints. There are lots coming up in the market. But still their efficiencies, the 3rd generation efficiencies are still very low. The monocrystalline has at the lab levels at least 40% of the efficiency. Okay. Then you have locational factors, the grid availability, microclimate, dust conditions. So all these, these are various factors which influence the PV performance. So these are some real buildings which used PV as their building envelope. So I have taken the cases like this is right very next in Sadashiv Nagar near Bangalore in IISc. So the roof itself is the PV panel. So you don't have anything underneath that. So if you see here, the skylight is the PV panels. So you can have the play of shadow and light and shadow and things like that, and you can come out with wonderful designs. So when you kind of have this as your envelope, you have to have your building functionalities to be taken care of. The weather protection, it protects from sun. The noise protection, it gives a brilliant view, and it has thermal insulation. You have visual cover. Okay, so you have different types like the way I showed you in the previous picture. You can have transparent, opaque sheets but behind in such a way that you can have the visual cover, and it has electromagnetic shielding, and it is safe. So now when I'm talking of the panel becoming the building envelope, I need to have certain building functionalities as mentioned. It has to be taken care. Structural rigidity, so which means the protection from external threats. Thermal regulation, so provision for thermal comfort and indoor living environment. So then I have daylight, which has to be taken care of, acoustics, insulation, aesthetics appeal, and electricity generation. Now, this is the new functionality which is added to the list of already existing building envelope functions. From an energy perspective, if you just look at this, is on the right hand side, you have a graph which shows the various appliances, how much a typical house would consume. So you have for mechanical ventilation, that's fans and your AC together, approximately 40%, right? 41% is what we consume energy for. So now, you're building, like, why the energy is basically like after giving all these functions, the whole my study has scoped down only to the thermal performance or the climate responsiveness of this particular material. Why? Because your energy consumption of the building is directly dependent on your thermal performance of the building, which is nothing but the climate responsiveness of that particular building. So now what affects the climate responsiveness of a building? So you have the solar exposure. So you understand the latitude, longitude, where is your building placed and things like that, and time of the day. All these sub-factors gives the solar exposure. Now this in turn affects the climate of that particular locality. So that comprises of, again, humidity, solar radiation, rainfall, temperature and wind patterns. Then you have your microclimate. You have 3D objects. You have a lake in front of the building. You have a hillock, trees. What is the ground covered with? A ground covered with snow has a different reflectivity as compared to a ground covered with grass, right? And why is all this important? Because PV has high energy. PV has a very low energy density as compared to another coal power plant. So what is energy density here? So when I say the amount of land or the area of land which I need to produce 1 kilowatt hour from a PV panel is much higher than as compared to a coal power plant. So it's approximately 1:10 ratio. So whatever electricity I'm generating, and if I'm not comfortable in that particular house and I spend in reverse for the HVAC to run, so I lost the whole purpose of having the PV fixed in the first place, right? So I need to there is a balance which I need to strike where my PV performance is not compromised, my building thermal performance is doing really brilliant. And that's when I call, yes, this house is really green. It's really meeting its purpose. So a quick understanding of what climate responsiveness is. You have at the site level, you have the macroclimate and microclimate, and you have your building orientation, which is important, the sun path, the solar radiation on different surfaces of your building. And then you have your building envelope. So what kind of material you're using, what are the types of walls and roofs, the area, type of glazing, the wall to window ratio. So all this will impact your heat transferred into the building, into the indoors of the building. So which is nothing but, again, your climate parameters are important here. So, so getting into the depth of now we understand what is climate responsiveness. But for any study, what is important? How do we quantify it? That's more important, right? So when you have your building elements, roofs, walls, and fenestration, and then you have your types of thermal performance. You have air-conditioned buildings, non-air-conditioned buildings, and you have hybrid systems. You kind of like the Jugaad-wala system in India. We open the windows, then it's comfortable, and when it's really hot, then we close the windows and use the air conditioning. So this is called the hybrid system. So what I have done is, like, the various metrics the various ways of quantifying this energy consumption is what I'm showing you on the right hand side of this. So where the building element, like, element wise study, you have opaque or transparent, then you have different, whether it's a steady state study, then you have the U value, resistance, TPI. These are time lag, decremental factor, which we all would have studied in our climatology. When you want to study about the whole building, this is at a building in an element level. So for a roof, you study the U value, maybe like, one diffusivity, the material properties, all these come under the element level. Whereas when I'm understanding the whole building level, there are certain studies, there are certain quantifications which have come up. Like in India also, we have this tropical summer index. Okay, but there is a lacuna. But these are under the steady state condition for a whole building, but there's nothing for a dynamic state. Okay, so this is one gap which we identified in this study. So we have come out with an index which in the flow, like in the further slides, we will discuss in detail. So till now, a quick snapshot of what we understood. So building and PV interaction, what is important? There are design constraints that we have to understand for maximizing both the PV performance, and at the same time, we have to maximize the climate responsiveness. Similarly, the energy output from PV system captures the influence of maximum variables affecting PV output. Okay. So we kind of, PV is pretty straightforward. We understand that because we say, okay, the electricity generated is the measuring metric for measuring the PV performance. But for the building, as I mentioned, we don't have, there's a big gap there. And climate responsiveness has not yet been quantified effectively. A general parameter is essential for the evaluation purpose. So this is where the snapshot of what all we understood till now. Going further, now can we take a proxy of the thermal comfort in the building as for a climate responsiveness for the building? So a provision of thermally comfortable indoor living conditions for the occupants in a cost-effective manner. Can we understand this? So when I'm using BIPV, so the three main purposes now: aesthetics, climate responsiveness, structure, and the value addition for any building envelope. We kind of look into these three things, right? Climate responsiveness, structure, and aesthetics. Along with it, BIPV has an advantage. A feather in the cap is electricity generation. Now, in climate responsiveness, what are the three main important things? That's light, daylighting, ventilation, and thermal comfort. Now, we are specifically talking of the electricity generation. So, we are talking of the plus and minus of energy. So, we need energy from the building side, and we are generating electricity from the building itself. So, we are trying to understand this equation in the big circle of society. That is for the people. We have various types of buildings, right? So you have detached houses, the semi-detached house, terrace houses. So, and you have low density, medium density, and high density. So a small attempt was done here where we can say, okay, what kind of issues we would face and which facade we can install PV. So that's where we just saw this, the housing classification, and we tried to understand, okay, is it really possible or not possible? So when you look at, like, the solar radiation intensity is high in roof integrated, whereas in facade integration, you have, it's very low. The area availability is low for a roof. For a tall structure, you have lots of facade area. So it depends, right? The system accessibility, easy to clean and maintain is for a roof, whereas in a high tall towers, it's difficult to clean and maintain it. Similarly, visual appearance may not be easily displayable when I'm installing, when I want to show that I'm a, like the way you have your EV cars with, green car and all that labeling, and you have a different color number plate. Like that, I want to show off on those lines. I can't do that when it's on a roof integrated system. But whereas when it's facade integration, it can impact. It has a very good visual impact. So similarly, BOS requirement, when you have it on the same surface, the tilt, everything remains same, the requirement is low. Whereas when you have different surfaces, different facades having PV integration, then you have a lot of equipment or instruments you need to buy to produce electricity. So again, what another attempt was made, like, how if you have high income and low density, what kind of buildings you stay. So we have say, okay, we have gated communities or villas. Okay, so in the interest of time, I'll just explain one. And where we have exposed roofs, since it's a high income and low density, you have villas, you have more exposed roof area. So with less vegetation, so you have approximately 75 to 150 square meters of rooftop, and you have, but the other side is you have high energy demand over here. And then you have low heights, high vegetation, shading is an issue. Okay. So most of you know what is the definition of thermal comfort. So it's a state of mind that expresses satisfaction with the surrounding environment. So I am comfortable. I'm not feeling slightly cold or slightly warm, but I am neutral to the environment around me. So when your body metabolism is allowed to dissipate, thus maintaining your equilibrium with your surroundings, we define it as thermal comfort. And why is it important? Because it affects the performance and productivity of our work. So it's a subjective. I might feel comfortable now, but my person sitting next to me might not be comfortable. So this study is not now, it's from 1923. There are various indices which are coming up, and there are different parameters which are being studied. So, but the most suitable for our study here is the ASHRAE revised 55 model. Why? Because this takes into consideration the outdoor ambient temperature, especially for naturally ventilated buildings. So coming from Bangalore and Indian conditions, where most of the buildings are naturally ventilated, so this is the most apt model which can be used for the study. So this is on the principle of that your indoor temperature is dependent on your outdoor temperature, which they have done across some 21,000 people across the globe, and they have come out with this formula. So what we have done is we have taken a roof integrated, as I showed you in the first picture, the roof integrated at IISc Bangalore. We have put a temperature measuring, dry bulb temperature measuring instrument in the room, along with it the RH, relative humidity, and we measured across the year. So this is the data. So we have put the maximum temperature and minimum temperature and acceptable range. So this people have given that the acceptable range, which is like if you see this chart on the right hand side top. So you have, based on your outdoor temperature, they gave you this gray area is where 90% of the people are comfortable. And this extension on the sides, that area where 80% of the people are definitely comfortable in that zone. So what we have done is we plotted all the maximum and minimum temperatures on the graph. And we see all these spots, you can see the red dots and the blue dots, they are always outside the comfort zone, except for few months, right here. So, and apart from that, there are certain factors, discomfort factors we have studied, and we understood that it's definitely, these are like within the range, and only the radiant temperature asymmetry, that is the heat, which is every body radiates heat, right? This we studied in 10th physics. So when the roof starts or the PV panel starts radiating heat or cold, when it's too cold, it starts radiating that. So then your body, like there is an asymmetry of the temperature, radiant temperature. So that is out of the beyond the bearable range. So, we understand degree discomfort hours. The simple way is like, okay, the number of hours when I'm in that particular room, how many hours are discomfortable. So this is the simple calculation, right? When every hour, whether I'm falling in that range or not is what we have checked. And the BIPV building has a DDH value of 4,552. So in a year, we have approximately 8,064 hours, right? How many? So 24 into 365 if you calculate. So of that, almost 50% of the time we are out of the comfort range. But another reason of why I said that this DDH is not suitable, like in the earlier when I mentioned the whole building study, we have a gap. It's not DDH which we can simply use because it's not effective. Because when I am saying my comfort range is between 21 and 29, and even if I'm 30 degrees centigrade, if the temperature is 30 degrees centigrade, I still say I'm discomfortable. Even if it is 40 degrees inside that room, it's still discomfortable. So you're not able to measure that intensity. So what we have done is we have worked out a new term which we have coined. We have coined a name as thermal comfort energy. So it takes into consideration the difference of the temperature from the comfort zone also. So it's good understanding the concept itself. Any more details we can get in touch offline. So when I am using PV, not only that, there are certain other energy requirements also which have to be taken care of. So like building classification determines the type of BIPV system, whether it has to be roof integrated or facade integrated, and what kind of electric load that I can cater to. So if I can have a microwave or a geyser or motor, all these can't work on PV directly. Okay, so because the initial power requirement and all will be so very high. So what kind of equipment you use at home is also equally important. So provision of thermal comfort, which is like all this while we have discussed, is very important. And more than that, economics. Everybody starts asking, right? Is it really economically viable or not now? Right? So quantification of thermal comfort is not yet available. So where we have kind of given a proposal for that. And we have roof integrated PV is not thermally comfortable according to the ASHRAE revised 55, given the annual temperature range of 21 to 29. Only like August is the comfortable month in Bangalore. So the other alternative, like as I mentioned, the kind of equipment you use at home now, like say we see a simple calculation which we tried doing here. So we have a lot of appliances at home. So tube lights of 7, fans of 4, and CFLs of 2, and 1 TV, 1 fridge. And approximately, if you say you're using it for these many hours, and the conventional wattage would be 40, so 100 for fans, and CFL 20, TV is approximately 120, and your fridge 208. But when you use energy efficient equipment, right? So then you have tube lights which run on 10 watts. So as compared to 40, you are consuming very less energy, right? So conventional energy, if I'm using 13.8 kilowatt hour per day, if I'm using energy efficient consumption would be 3.7. So these are all things which have to be taken care of, right? When I'm using my building material as PV. So I need to understand all. So it's like I just don't put up my PV panel on top of my house and say, yes, I am going green, but when it's not actually serving the purpose. So you need to take the impact of this energy efficient appliances will have a huge impact on your PV load calculation also. So this is some graphs and, just getting into a little more detail of how and when and things like that. So when I just, to give a snapshot. So in the month, if you see the blue color line on the top is the inside temperature of a PV building, whereas the outside temperature is much better. This is, I'm talking about a direct PV roof. So then we did some kind of, is really PV the culprit? So such kind of doubts in research, it's very important to question everything. So what we have done is, like certain period, so we have measured the temperature across the room, and we understood that the cell temperature is just following the trend of the solar radiation. So if you see the solar radiation, that is this line on the top, blue double line, you see the cell temperature, that is this blue dotted line. It's just following the same trend. So you don't have any thermal lag or any decremental factor here. So your room temperature is exactly following the same trend. So we have done a simple experiment. So when we understood the roof is the culprit, so we just, during the peak time, hours of sunshine, we poured water on the PV panels so that the PV efficiency is not disturbed. So the green line, if you see, so as I told you, as the temperature increases, the efficiency drops. So as the panel was getting heated up, the efficiency is dropping down. Whereas when we started pouring water, the cell temperature has fallen down and the PV efficiency has gone up. And in the same contrast, like if you see, the room temperatures have dipped down during that same time out. So this further led into understanding like what the material properties, which is very important, that is a thermal mass. So which is for a PV panel is 0.0083 joules per Kelvin meter square. Whereas the decremental factor is 0.0001. So this against, when you compare this thermal lag is 1 point, it's hardly like within the temperature outside changes within no time, the inside temperature also changes. Whereas as compared this, if you just compare with a brick or a concrete where it is 0.37 is the thermal mass. Whereas concrete is 0.74 joules per Kelvin meter square. RCC is 0.2. So the thermal mass is the culprit for the PV panels to perform like that. So we have taken a building simulation software and we tried to understand. So if you see the graph on the top, the blue line is the PV roof's temperature, and we just removed the PV roof and put a concrete roof there and understood. So this orange dotted line. So if you see the peak, so for a concrete slab, it would be something around 27, 28, as compared to a PV panel, the inside temperature is something around 35, 37, 38 times. Okay. So a rough calculation, if I just use PV, which causes 2.7 times more energy consumption than a concrete slab. So the long story in short, climate responsive is very much needed when I am trying out a new material, whether it's suiting that particular location or not is very important, and especially for PV, because PV has low energy density. So as compared to like when I am getting the same electricity from a coal power plant, though I'm paying money for it, and this also, this breaks even with a payback period of 5 to 6 years as of now, with this present technology. So we need to evaluate the BIPV systems based on not only the electrical performance, but also the building envelope functions also play an equally important role. So the thermal performance of any building envelope is of paramount importance when you talk in terms of energy of the building, energy consumption of building. This is very, very important. So what kind of appliances you use at home, so what kind of material you use for the building envelope, all these play a very important role when your building's energy or the thermal performance of a building is calculated. I stop here. Thank you so much. So these are a couple of publications where we in depth dealt into all these topics. So I tried to squeeze it into a small package. So for more details, we can read these papers. Thank you.